Hi, in this video, I'll explain and demonstrate proof by induction. First, I'll show how it works. Then I'll give three examples, one in algebra, one in geometry, and one more that's kind of advanced in linear algebra. Let's start. Suppose there's a row of lockers numbered 1, 2, 3, etc. We want to open the lockers. We would need a key to all of these lockers, right? Well, luckily, suppose we have this rule. The rule says if we can open any locker K, then you will also be able to open locker K plus 1. Maybe because locker K contains a key to locker K plus 1. And since that's true of any K, it means locker K plus 1 would contain the key to locker K plus 2. Basically, a rule that says if true for K implies also true for K plus 1. Then what does it take to open all the lockers? Well, all it takes is to open the first locker, right? Then applying the rule that says once I open locker K and I can open locker K plus 1, it means from 1, I can open locker 2. Applying the rule again, from 2, I can open locker 3. And then locker 4, locker 5, etc. in a chain link kind of manner. That means we can get into all lockers if we have these two things. Number one, that we can open the first locker. And number two, that we're guaranteed that once we open locker K, we can open locker K plus 1. The first step is called the base case. The second is called the inductive step. Notice something important. The inductive step by itself does not open any locker. The base case is what starts the chain. Without access to the first locker, we could know that every locker contains the key to the next and still not be able to get into any of them. That's the principle of mathematical induction. We use it to prove that a certain statement involving integers n greater than or equal to a certain value. Number one, the base case. We prove that the statement is true for a starting value, usually n equals 0 or n equals 1. That's the first locker that starts the chain. Number two is the inductive step. We prove that if given that the statement is true for n equals k, then it must also be true for n equals k plus 1. That's a linking rule that says each locker can open the next. There's a stronger version of induction, but it's not part of this video. I'll mention it briefly at the end of the video, but I won't go into it. Here's the template of a proof by induction. It's most applicable to proving a statement about integers n greater than or equal to some number a, usually 0 or 1. You start with checking the statement is true for the base case n equals a, the starting value. Next is to prove the inductive step. Write down the assumption, assuming the statement is true for n equals k. This is called the inductive hypothesis. We will prove that the statement is also true for n equals k plus 1. The proof should make use of the case n equals k. If your proof doesn't make use of the case n equals k at all, you're missing something. Once we've proven both the base case and the inductive step, we're done. Let's do some examples. I will do one with algebra, one with geometry, and then one with linear algebra. Example 1. Prove that for all integers n greater than or equal to 1, 1 plus 3 plus 5 plus all the way up to 2n minus 1 equals n squared. 2n minus 1 is an odd number. What this says is that the sum of consecutive odd integers is always a perfect square starting from 1. And in fact, it is equal to the square of how many odd integers we were adding. Before proving, just for fun, let's try a few examples. N equals 2. Two odd numbers add up to 4, and it's equal to 2 squared. N equals 3. Three odd numbers add up to 9 equals 3 squared. Let's jump to n equals 6. 6 odd numbers add up to 36 equals 6 squared. That's pretty cool. Let's now prove it by induction. First, we write the word induction. Proof by induction. It is always a good idea to actually write down your proof method to make it easy for people to follow along. You will see that professional mathematicians always say it, proof by induction or proof by contradiction. Base case, n equals 1. That means one odd number. The left-hand side is just 1. The right-hand side is n squared, and it's equal to 1 squared, which is equal to 1. They are equal. The base case is met. Now let's do the inductive step. This is how you write the inductive step. The first line should always be assume true for n equals k. Remember that k represents an arbitrary integer. We're not choosing a specific value of k. We're proving that the inductive step is true given any k value. In terms of the locker analogy, we're not talking about a particular locker. We're saying that if we can open any locker k, then we can open the next locker k plus 1. The k in this step is an arbitrary integer. Now we write the inductive hypothesis. That is, we write the statement from the question, just write it down with k instead of n. In our case, it's like this. 1 plus 3 plus 5 plus ... plus 2k minus 1 equals k squared. Next, clearly state your target. What the statement looks like when we substitute k plus 1 in place of n. We write that we want to prove 1 plus 3 plus 5 plus all the way up to 2 times k plus 1 minus 1 is equal to k plus 1 squared. Don't forget to use parentheses around the k plus 1 as needed. Now let's do the proof. The key to proving the inductive step is that since we're given this assumption, I'm circling it, we should rewrite the second equation in such a way that it contains the assumption inside of it. We're giving the k case for free. We should make use of it. I look closer at the left-hand side here. It is the sum of k plus 1 odd numbers. Wait, but that means before we get to k plus 1, we'd have to go through k odd numbers first to get to k plus 1 odd numbers. So before the value 2 times k plus 1 minus 1, we would have, look, 2k minus 1, right? Before k plus 1 is k. Let's drop the parentheses. And now recognize this beginning part here. We know what it's equal to. This beginning part is the same as the left-hand side in our inductive hypothesis. We have the assumption, the hypothesis, that it is equal to k squared. That means we can plug it in. All of this is equal to k squared there. Now expand the algebra. K squared plus 2 times k plus 1 equals 2k plus 2 and minus 1 equals k squared plus 2k plus 1, which is k plus 1 quantity squared, which is equal to the right-hand side. The inductive step is met. Since we've established both the base case on the left and the inductive step on the right, we're done. You can end your proof by writing QED, which is Latin for which was to be demonstrated. is an abbreviation that we traditionally use to mark the end of a proof. If you want to, you can write a longer sentence like this, but it's not necessary. Therefore, the statement is true by induction. All right, let's move on to example 2, geometry. Prove that the sum of the interior angles of a convex polygon of n sides, n greater than or equal to 3, is n minus 2 times 180 degrees. First, let's illustrate what this means. It's about a polygon and all the interior angles of it. If this polygon has n sides, then the sum of all those angles will add up to n minus 2 times 180 degrees. Some of you may have proven this in your geometry class where you divide the polygon into triangles. Each triangle has 180 degrees. And then you count the number of triangles, which is n minus 2. So the total is equal to n minus 2 multiplied by 180 degrees. That's a nice proof, and it's actually related to the proof by induction that we'll do here. Let's go. First, we write the words, proof by induction. Base case, n equals 3, because in the question, the starting value for n is 3. When n is equal to 3, the polygon is a triangle. For a triangle, the sum of the angles is 180 degrees. And n minus 2 times 180 equals 3 minus 2, which is 1, times 180 equals 180 degrees. The formula works, so base case is true. Now the inductive step. First, the hypothesis. Assume that the formula is true for n equals k. For convex k-gon, the sum of the angles is equal to k minus 2 times 180 degrees. We will prove for n equals k plus 1. That means for convex k plus 1 polygon, the sum of angles is k plus 1, then minus 2 times 180 degrees. Just plug in k plus 1 in place of n. Simplify the algebra, k plus 1 minus 2 is k minus 1, so k minus 1 times 180 degrees. The key to practically all proofs by induction is, because we're given the case that n equals k is true, we want to incorporate it inside the case n equals k plus 1. Here on the left, we're assuming this formula is true if there are k number of sides. We want to incorporate it inside the polygon on the right that has k plus 1 sides. Remember the proof you did in geometry where we divide things by triangles? Let's try to create a triangle in this new picture as well. What happens if we draw this line? Then on one side of it, it creates a polygon that one side fewer. So it has k sides. And then over here is one triangle. By the way, geometrically, here is where being convex matters. The polygon has to be convex to guarantee that the diagonal, the line we draw, stays inside the polygon and cleanly splits it into a triangle on one side and a smaller polygon on the other side. And all the angles of the large polygon, the sum of those angles, is equal to the angles of the triangle plus the angles of the smaller polygon. The angles of the triangle add up to 180 degrees. The angles of the smaller polygon with k sides, we know from the inductive hypothesis, is equal to k minus 2 times 180 degrees. Total sum of angles of the large polygon, therefore, is equal to the sum of the triangle plus the sum of the k-gon, which is equal to 180 plus k minus 2 times 180. Equals. Let's factor out the 180. We get 180 times 1 plus k minus 2, which equals 180 times k minus 1. And that's exactly what we want. Both the base case and the inductive step are met, QED. Next example, I'll jump to an advanced topic and do linear algebra. This is for students who have seen matrix multiplication. Example 3. Let D be the 2 by 2 diagonal matrix, like that, with AB down the diagonal. Prove that for all integers n greater than or equal to 1, D to the power n is equal to diagonal matrix with A to the nth and B to the nth in the diagonal. We'll prove by induction. First, we write the words. Proof by induction. The base case is n equals 1, because that's what the question says. When n equals 1, on the left-hand side, d to the power n is equal to d to the power 1, which is just d. While the matrix on the right-hand side is a to the n, which is 1, and b to the n, which is also 1 down the diagonal. And that's just ab down the diagonal, which is the matrix D. They match. So the base case is true. Now let's do the inductive step. The hypothesis. Assume true for n equals k. Just write down the statement with k in place of n. Now we write what we want to prove. We want to prove the statement is true for n equals k plus 1. Write down what it means. We want to prove the statement with k plus 1 in place of n. Now let's work on the proof. How do we get the d to the power k inside of d to the power k plus 1? Aha! D to the power k plus 1 is equal to d to the power k multiplied by another d. And we know what d to the power k is equal to by assumption. And we know what d, the separate d, is equal to, is given in the question. So we plug it in. It's a 2 by 2 matrix times a 2 by 2 matrix, so it will equal a 2 by 2 matrix. Let's take one position at a time. Let's take this first position, position 1, 1, equals row 1 times column 1. And that is equals to a to the k times a plus the other is 0 times 0, so that's just 0. And the whole thing is a to the k plus 1. Moving on to this position, position 1, 2, equals row 1 times column 2, dot product with column 2. That's just 0 plus 0, so equals 0. Moving on to the next position, position 2, 1, equals row 2, dot products with column 1. That's just 0. 0 plus 0 equals 0. Finally, this last position, position 2, 2. So it's equal to row 2, dot products with column 2. That equals 0 plus b to the k times b. The whole thing equals b to the k plus 1. And that is equal to what we want to prove. The inductive step is met. Both the base case and the inductive step are met, QED. Let's summarize. Proofs by induction are helpful when proving that a statement is true for all integers n greater than or equal to some initial value a. Often they are statements or theorems about all positive integers or all non-negative integers. Like all proofs, you should start by understanding exactly what it is we're proving. Like for the polygon question, you want to draw a diagram or something to understand what the question is about, and understand how that statement includes the integer n. The process is, first we write the word by induction or proof by induction. We check the base case, the smallest n applicable to the statement. Next, we prove the inductive step. We write the words assume true for n equals k. We write down that assumption by plugging in k for n in the statement. That would be our inductive hypothesis. Then we write what we need to prove. We want to prove, then plug in k plus 1 for n. Proceed to do the proof, right? And then some proofs may be easier and some may be harder, but in proof by induction, it's always a good idea to try to find the case n equals k inside of the case n equals k plus 1. If the proof never uses the n equals k hypothesis or assumption, something is probably missing. All right, here's an even shorter summary of the summary. Number one, prove the base case. Number two, clearly state the inductive assumption when n equals k. And number three, use it to prove the case n equals k plus 1. That's it. Now, before leaving, let me just give you the stronger version of induction. In the regular version of induction that we've been using in this video, we assume that in the inductive hypothesis, that the statement is true for n equals k. In the stronger version of induction, instead of assuming the statement is true for just one value n equals k, we assume that it's true for all n less than or equal to k. That stronger assumption gives us more values to work with in the proof. In terms of the locker analogy, instead of assuming we've opened locker k, we're assuming we've opened all lockers 1 through k. This is a stronger tool that we may need when proving the k plus 1 case, when it depends not on just k, but on earlier values as well. But that's a story for another day. Hope this helps. Any questions or comments, put it in the comments section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.